going to continue working with combustion analysis today, except today we're going to hit a couple of situations where maybe things didn't turn out quite so nice, and we've got to figure out an alternate way to solve some of these problems. So the first sample problem that we're going to work is another metal oxide problem, very similar to the one that we worked a couple of days ago. In this particular case, we are burning vanadium metal, and the symbol for vanadium is V. Vanadium metal is heated in air to form an oxide. So if 0.3456 grams of vanadium reacts with oxygen to achieve a final mass of 0.6170 grams, what is the empirical formula of the oxide? So I'm not going to really work this one any differently than the way that I worked it before. So I'm going to take 0.3456 grams of vanadium. For every 1 mole of vanadium, I have 50.94 grams. That comes from the periodic table. So when I cancel out grams, I will end up with 0.000, make a zero there, 6784 moles of vanadium, okay? Because it's an oxide and I know that there weren't any other products made, I know that if my final product was 0.6170 grams of product, and I know that 0.3456 grams of that was the vanadium, the remainder of it had to be oxygen. So that gives me 0.2714 grams of oxygen, okay? So now if I have grams of oxygen, I need to turn it into moles of oxygen. So I'll have 0.2714 grams of oxygen, put that over 1. In 1 mole of oxygen, there are 16 grams of oxygen, so grams cancels out, and that gives me 0.01696 moles of oxygen, okay? Now again, like we did before, here I have moles of vanadium and moles of oxygen, okay? I'm going to take the smaller number and divide it into all of them so I can get the smallest whole number ratio. So in this case, I'm dividing by this number, 0.006784, and I'm going to divide this one by 0.006784. Only this time when I do it, it doesn't come out so nice, because this gives me 1, which is very nice, but this gives me 2.5. 2.5 isn't close enough to 3 in this case to be able to round it up, because that's going to throw my ratio way off. So what am I going to do with this? Well, 2.5, if I multiply that by 2, and I multiply this one through by 2, my ratio then goes up to simple whole numbers. This one becomes a 2, and this one becomes a 5. So therefore, my final answer is going to be V2O5 for my formula of vanadium oxide. There are all sorts of really nasty wrinkles that can come up with this, but I will tell you that you're not going to have anything any more complex than having it end up with a 0.5. If it would have ended up like in a 0.33 or a 0.67, that's 1/3 and 2/3 in decimal form, so you could multiply through by 3. But I don't recall that in any of the problems you're going to be working that it even gets that complicated. I think the most complicated thing you have, excuse me, where it's going to end up with a 0.5 on the end of it. Okay, so let me get rid of this, and then we're going to work the other problem, which I alluded to a little bit the other day. And that's if you have combustion analysis of a compound and it's not just carbon and hydrogen, and you end up with something else in addition to that as well. So how am I going to work that kind of a problem? So if you look at the second problem that we're going to do today, you've got 0.25 gram sample of an unknown substance was burned in excess oxygen to produce 0.3664 grams carbon dioxide and 0.15 grams of water. There were no other products. Okay, that's very important to know that nothing else was formed besides that carbon dioxide in that water. What is the empirical formula of the unknown substance? Okay, the wrinkle in this one is that they did not tell me that it was only carbon and hydrogen in the compound. And if I produced carbon dioxide and water, well, what's carbon dioxide contain besides carbon? Oxygen. What's water contain besides hydrogen? Yeah, oxygen. And so both of those contain oxygen. They're both in different parts of the compound, or they're both in different parts of the products, the combustion analysis that was made. And so what am I going to do with that? Well, we're going to start it the same way that we started it before, and we're going to start out with this carbon dioxide. So I've got 0.3664 grams of carbon dioxide, and just like before, I've got to change that to moles so I can figure out how many moles of carbon I'm going to have. So in 1 mole of carbon dioxide, there's 44.01 grams of carbon dioxide, and that will give me 0.0083325 moles of CO2. Okay? Again, this isn't any different from what we did the last time. This is the same thing. I know that if I have this number of moles of carbon dioxide, I'm going to have the same number of moles of carbon. So I'm also going to have 0.0083325 moles of carbon. Okay? So that's the same as before. That hasn't changed. Now let's look at the water. Okay? I'm intentionally leaving a little bit of space here, so if you're writing this down as we go, make sure that you leave some space here, and I'll explain why in just a minute. Okay, so I've got 0.1500 grams of water that were produced, and so we'll turn this into moles. 1 mole of water is 18.02 grams of water. And so when I turn that into moles of water, I have 0.0083324 moles of water. And like we said before, if I have this many moles of water, I have twice as many moles of hydrogen because this subscript of 2 tells me it's a 2-to-1 ratio. So I'm going to have 0.01665 moles of hydrogen. Okay, so far I have my moles of carbon and I have my moles of hydrogen. But my oxygen ended up in 2 different places. Part of it's here and part of it's here. Well, what's the simplest way to figure this out? Because part of the oxygen could also have been used for combustion purposes, so I need to make sure that I'm only going to include the amount of oxygen that was actually within the compound itself when I started. So in order to do that, I'm going to have to subtract off the amount of carbon and the amount of hydrogen I had. Okay, so I'm going to take this number of moles of carbon, 8325 moles of carbon, and I'm going to convert that to grams. So in 1 mole of carbon, there's 12 point, well, if I could read it, 12.08, I believe, grams of carbon. And so that's going to give me 0.0998 grams of carbon. Okay? I need to do the same thing with the hydrogen. So if I have 0.01665 moles of hydrogen, I'm going to convert that to grams. In 1 mole of hydrogen, there's 1.01 grams of hydrogen, and so that's going to give me 0.01682 grams of hydrogen. Okay? So my original compound was 0.2500 grams of compound. Okay, that's how much I started with. I'm going to subtract off 0.0998 grams of carbon, and I'm also going to subtract off the 0.01682 grams of hydrogen. Okay, so this was the whole compound, this was the carbon, this was the hydrogen, and so when I subtract that, that gives me 0.1332 grams, and that's grams of oxygen. Okay, so that's how much oxygen was in my initial compound. If I have that many grams of oxygen, I can now convert that to moles of oxygen. So in 1 mole of oxygen, there are 16 grams of oxygen. And so when I convert that, I'm now going to have 0.008325 moles of oxygen. Okay, so if I look here now, here's your moles of carbon, here's your moles of hydrogen, here's your moles of oxygen. We're going to do just like we did before, and we're going to find the smallest number. As it turned out, the moles of oxygen and the moles of carbon were the same. This is the bigger number. So if I divide this by 0.008325, I divide this by 0.008325, and I divide this by 0.008325. This gives me 1, that gives me 1, and this will give me 2. So the simplest whole number ratio is going to be CH2O. Okay, now you may be looking at this saying, well, how come I couldn't just take this, I couldn't just take moles of oxygen from here and moles of oxygen from the water and do it that way? Well, the reason is because you've got to have oxygen for burning, and so it may not always be the case that if you do that oxygen, that's going to be the same amount that was in the compound. Normally to set something on fire, to start it burning, you've got to have some other oxygen that was in the air. So you cannot make the assumption that all of that oxygen that's in the carbon dioxide and then that's in the water came from the initial carbon-containing compound that you were burning, because when you have combustion, you've got to add in extra oxygen for the burning to happen. So more than likely, the amount of oxygen that you've got here is not going to match the amount of oxygen that was in the compound, so that's why you can't do it that way if that question happened to come into your mind, okay? So again, this process is really not that much different from what you've already learned. The difference is that once you have moles of carbon and moles of hydrogen, you're going to have to also convert it to grams and subtract it from the original amount so you know how many grams of oxygen were in your compound. Then convert that to moles, and then you can find the whole number ratio for the whole thing.